Hello, this is Dr. Michael Hassan, the recipient of the IEEE Outstanding Engineering Educator Award. My YouTube channel is The Engineering Doctor, and this is the course titled Digital Logic Design or Digital Systems or Digital Electronics. This is the first lecture of Chapter 2 and lecture number 5, Logic Gates. Disclaimer for you to read. There are many references in digital logic design, including but not limited to Digital Logic Design by Hassan, Fundamentals of Digital Logic with VHDL Design by Brown and Franzik, Fundamentals of Logic Design by Ruth, and many others. The contents of this lecture are: we'll talk about logic gate, inverter or NOT operation, AND operation, OR operation, NAND operation, NOR operation, exclusive OR operation, exclusive NOR operation, Boolean, also known as switching functions, combinational network synthesis, combinational network analysis, constructing the truth table, and the complement of a function. Logic gates. Boolean algebra was first introduced by George in 1854. His book, An Investigation of the Laws of Thoughts, laid down the foundation to the calculus of propositions, known as Boolean functions and algebra, which are based on true states, true and false. Boolean functions are known as switching or logic functions or logical functions. All Boolean, switching, or logic functions can be exclusively implemented with logic gates. This is why logic gates are very important in the implementation and design of any binary system. Why binary? Because we have two values, true and false. The truth table. Logic gates and logic functions are defined by a truth table. This is a table which lists all or most possible combinations of input variables applied to a gate or to a digital system. The maximum number of combinations, i.e. rows, in a truth table is 2 to the power n, where n is the number of input variables. So for instance, if n is 2, we'll have 2 to the power 2, which have 4 combinations, 0, 0, 0, 1, 1, 0, and 1, 1. And if n is 3, we'll have 2 to the 3, which is 8 combinations, 0, 0, 0, 0, 0, 0, 1, way down to 1, 1, 1, 1. For n3, we'll have 8 combinations, 0, 0, 0, 0, 0, 1, way down to 1, 1, 1. So we have 3 variables. If we have 4 variables, well, combinations start with 0, 0, 0, 0, 4 variables, 0, 0, 0, 1, way down to 1, 1, 1, and so on and so forth. Each input variable can be either 0 or 1. The input combinations are usually listed in binary counting order. So, for instance, for 2 input variables, we list them as 0, 0, 0, 0. The output of logic gate is often labeled with F, which stands for function. The output function F can be either logic 0 or logic 1 for each input combination, or for each combination of inputs. So an inverter or NOT operation. The prime sign, complement sign, in Boolean algebra represent complementation, also known as negation or inversion. So the electronic circuit which performs inversion is referred to as an inverter or NAT gate. The NAT gate is represented by the symbol shown in the figure. So we have a simple triangle and this circle. This circle signifies negation or inversion. So if I have A, the output will be F, which is the complement of A, or the inversion of A. The truth table of the NAT gate will have one variable, so we have only two values, 0 and 1. And the function will be the complement of the input. So the input is 0, the output function is 1. If the input is 1, the output F will be equal to 0. So as a mathematical equation, logical equation, we say F is equals to A prime, A bar. So the complementation or the negation or the inversion can be represented by the prime sign or by a bar on top material. AND operation. The multiply sign that in Boolean algebra indicates an AND operation or AND gate. The definition of an AND operation is as follows. 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. It looks like really decimal multiplication. The output F is 1 if and only if A and B are both 1. The symbol of AND gate is shown here in A with two input variables A and B, so F will be A dot B, or just we say AB, even without the dot. While the truth table is AB and the function F. See, when we fill the truth table, we fill the least significant bit, which is B, 0, 1, 0, then A, 0, 0, 1. If we have three variables, we fill 0, 0, 0, 0, 0, 0, 1, then 0, 0, 1, 0, 0, 1, 1. Then the third variable will be 4 zeros and 4. Okay, so in this case, we have only two variables, and the inputs are 0, 0, output will be 0, 0, 1, output is 0, 1, 0, 0, and 1 is 1. So the AND operation will be 1 only if all inputs are 1. In case of multi-inputs, more than 2, we need all inputs to be 1 for the output F to be 1. OR operation. The plus sign in algebra indicates an OR operation or OR gate. The definition of the OR gate is as follows. 0 or 0 is 0, 0 1 is 1, 1 or 0 is 1, 1 or 1 is 1. So the Boolean expression F, A, or B represent an OR operation, as we said, and the output F is 1 if and only if A or B or both are 1. The symbol of the OR gate is shown in A. We have two inputs, A and B, and the output will be A or B. And the same thing with the truth table. The function F will be 0 if two inputs are zeros, and it will be 0, 1, which is equal to 1, 1 or 0 is 1, and 1 is 1. This is the OR operation. Next slide is the NAND operation. And the NAND operation, NAND function, is a combination of AND and NAND functions. The output of a NAND gate is simply the inversion of that produced by an AND gate. So the output F will be 0 if and only if A and B are both 1s. Otherwise, F will be equals to 1. So this is the NAND gate symbol, and the circle again signifies inversion or negation. The truth table will have A and B. 0 and 0 will be equals to 1, which is the complement of the AND gate. 0 and 1 is 1, 1 and 0 is 1, and 1 and 1 is 0. The NOR operation or function is a combination of the OR and the NOT functions. The outputs of an OR gate are simply the inversion of that produced by an OR gate. The output F is 1 if and only if A and B are both zeros. Otherwise, F is 0. Like the NAND gates, NOT gates are functionally complete. So both the NAND gates are functionally complete or universal gates. That is, every switching function can be implemented entirely with gates. That's the true NAND gates. NAND gates are functionally complete or universal gate. That is, every switching function can be implemented entirely with NAND gates. So both NAND gates and NOT gates are universal gates. Again, the truth table actually for the NOT gate, F will be 1 if and only if both inputs 0 are 0. So A is 0 and B is equal to 0, and otherwise F is 0. In the symbol that we use here, A or B, then between parentheses, we must have parentheses to signify the complementation or negation for both combination of A or gate. It means it is an OR gate. If we have A without parentheses, we'll read it A or B not, and this is not true because will be a different function. So the parentheses are very significant. Exclusive OR operation, the symbol that we use is the plus sign surrounded by a circle. So A exclusive OR B is 1 if and only if either A or B is 1. Otherwise, A exclusive OR is 0. So it is clear that the exclusive OR operation assigns to each pair of variables its modulo to sum, as if we are adding. Let's look at the symbol of the exclusive OR. It's in A. This is a typo here, A exclusive OR B. And the truth table is what we get. 0, 0, F will be 0. The input 0, 1, F will be 1. If the inputs are 1 and 0, F will be 0. Inputs are all 1s, 1 and 1, and the output F will be 0. So it is a modulo 2 addition. 0 plus 0, 0, 0 plus 1, 1, 1 plus 0 is 1, and 1 plus 1 is 0. So this is F exclusive OR. This sign here is a plus sign surrounded by a circle. So A exclusive OR B will be F is equal A exclusive OR B. Now the exclusive OR has some properties, very significant properties that we will like to look at. A exclusive OR B will be B exclusive OR A. A exclusive OR B exclusive OR C will be A exclusive OR B, then between parentheses exclusive OR C, which is equal to A exclusive OR B exclusive OR C. A B exclusive OR AC will be A times or and B and C, the exclusive OR between B and C. A exclusive OR 0 is A exclusive OR 1 is A prime, A exclusive OR A is 0, and A exclusive OR A naught is 1. A exclusive OR B is A bar B or AB bar. Now I'll show you why this one is true. Now we can prove those easily when we study Boolean algebra, but I'll show you the value, the last value. A exclusive OR B is the value of F. When F is equals to 1, F is equals to 1 here in the second row and in the third row. F is equals to 1 when A is 0 and B is 1, and F is equals to 1 when A is 1 and B is 0. So what we can say, we can say f is 1 here or here. Okay? In the second row, when f is 1, a is 0 and b is 0. So we say the complement of a, which is a prime b. A prime because a is 0, which will indicates a prime, then b because b is 1. Here, this is called actually the minterm. It is a b prime. We will cover this later on in more depth, in depth. So a is 1 and b is 0, so it is a b prime. So f will be 1 here or here, so we say it is a prime b or a b prime. And this is how we get this switching function. So a exclusive or b will be a prime b or a b prime. Multiple variable exclusive OR operation is known as an add function, since an odd number of variables must be equal to 1 as a requirement for the output to be 1. So if we have n variable, we will need an odd number of variables equal to 1. Because as you know, 1 plus 1 plus 1, if we have 3 variables, is equal to 1. Because 1 plus 1, the modulo 2 addition is 0, plus 1 is equals to 1. However, if we have 4 input variables are 1s, those are even numbered, so the function will be 0. Again, here, actually, this is a circle and surrounded, plus surrounded by a circle. So a exclusive or b. The next slide will be exclusive NOR. The exclusive NOR, also known as equivalence operation, or exclusive NOR gate, or equivalence gate. So it is A exclusive NOR B, as you can see between parentheses, and there is the prime sign to signify complement. So A exclusive NOR B is equal to A equivalence B equal to 1 if and only if both A and B are equal and equals to 0 otherwise. So if they are equal to 0 or equal to 1, at that time the equivalence will be 1, otherwise it will be 0. Based on the exclusive NOR definition, one can formulate that A exclusive NOR B equal A exclusive equivalence to B, which is A exclusive or B naught, or A naught exclusive of B, AB, or A prime B prime. Or we can say A exclusive NOR B, it's A prime B or A B prime. This is the definition of the exclusive OR prime, which is A or B prime multiplied by A prime B, which is AB or A prime B prime. As you remember, just we took, since we have here 1, this will correspond to the midterm A prime B prime, and here actually the midterm is AB, so F will be 1 here or here, so it is F will be A prime B prime AB, or we can say AB or A prime B prime, same thing, and you can see the value of function F, exclusive NOR. The symbol is similar to the exclusive OR by adding a small circle here to signify complements. Again, there's a typo here. This is A plus surrounded by a circle B between parentheses, and we have prime negation symbol. Switching functions. A Boolean switching function f is formed by applying the basic operations, inversions, and OR to a set of n switching variables where n will be equal to 0, 1, 2, 3, and so on and so forth. The simplest switching functions are f is 0 or f is 1. This is a valid switching function because 0 means false and 1 means true. So this is a function. Now in TTL, how we implement this function is coming really in the next slide. I'll show you how to implement those two simple functions. But in TTL, 0 represents 0 volt. TTL stands for transistor logic, where F will be equals to 0 at 0 volt, and 1 will be equal to plus 5 volt. F can be a function of one variable A. And for instance, F as a function of A will be A, and F as a function of A will be A prime or A complement. So this is, we call it a buffer, and this is, we call it an AND gate or an inverter. More complicated function can be formed with two or more variables and logic gates, such as NOR, NAND, exclusive OR, and exclusive NOR, NAND, such as, for example, f of AB, this is two variable, it's A prime or AB prime. F of ABC, those are three variable function, is A or C or B, C prime. F of ABCD, four variable function, is A and C or B prime or B exclusive or D. So this is a four variable function. The next slide will talk about the construction of combinational network, how we synthesize combinational network. Now, what's the term network or circuit? Combinational network, combinational circuit, is a network or circuit that consists of combination of logic gates. So if we have any circuit with logic gates without memory, a memory usually generated when we have a feedback. So without feedback or without memory, the circuit or the network is called combinational network. Synthesis, it means building. It means construction. To synthesize a network, it means to build it by hardware means. So the synthesis of the function f is 0 and f is 1, we said f is 0, it means 0 volt. So we can take it to the ground. However, by taking a wire or conductor to the ground, we may generate actually a ripple or due to what's called transient response, may generate a problem. F is 1, the same thing, it's plus 5 volt. You cannot take the wire directly to plus 5 volt because this will generate actually a problem. To avoid this bouncing effect, switching effect caused, so we have a simple circuit here, a simple RC circuit with two inverters. So let's understand the circuit. This is not the only circuit. We may use actually a 555 timer also to generate, to construct the function f is 0 or f is 1. So that we have a plus 5 volt connected to 10 kilo ohm and connected to a capacitor 22 microvolt. So at steady state, the capacitor will be fully charged and the voltage here at this node will be equal to plus 5. Now when you take it to an inverter, you'll get a 0 volt here. When you take it to another inverter, you get a 5 volt, plus 5 volt. Those are TTL inverters. So the two TTL inverters will really are used to emphasize that the output be pure one. So if I have one, the switch is open, and the switch is open, for logic 1 here, or plus 5 volt, give me a logic 0 volt, and here you get a logic 1, so F will be 1 easily when the switch is open. Once I close the switch, you will get here 0 volt because the capacitor will be fully discharged. Any current will flow actually also to the ground from the plus 5 volt. So here I will get 0 volt, which will be complemented by the first inverter to logic 1, will be complemented to logic 0, so F will be equal to 0. The switch is closed. So by a simple circuit, we have a clean F0 and F1 depending on the switch, whether it is closed or Next slide. We'll have the synthesis of function with one variable, which is f is equals to a, or f is equals to a prime. So here we use a buffer. Okay, if the input a and we need f to stay to be a, f will be a. This is called buffer, or two cascaded inverters, or even number of cascaded inverters will give me f equals to a. However, if we use an inverter, not gate, if we have a, we can invert it where the output will be a prime, so f will be equals to a prime. And the circle here will signify inversion, while here there is no circle, so this is a buffer, and this is an inverter. And a and b, a will be the synthesis of the construction of the first function f is equals to a, and this is the synthesis of the second function f is equals to a. Let's look at more complicated example. If we take a function with two variables, a prime b or ab prime. So what this? This is an AND gate. This is a has to be inverted. So we need an inverter to generate a prime. Then we take it to AND gate with b. And this product term, we have a and b prime. So b needs to be inverted with an inverter. So then if we take those two to an OR gate, we'll generate f. That's what we did. We inverted a, we will get a prime. Sometimes without using an inverter, just as a simple, we can put a small circle at the input of the AND gate to signify inversion. Okay, and take a to a circle to the AND gate, or if we have the inverter here, to be more clear. So a inverted to a prime, and b, so the output of the AND gate will be a prime b. The same thing here, we have a and b inverted to b prime, and the output will be a b prime. So a b prime or a prime b or a b prime, take them both to OR gate, will give the value of function f. So this is a simple synthesis of a two input variable function of a and b. Now if we take a three variable function f, a, b of a, b, and c, as example, it is a or c or b, c prime. So we need an OR gate to OR a and c. So the first term, we'll take a and c to OR gate and we'll get a or c. We'll complement c to get c prime. Then we'll end it with b to get b, c prime. Then we will take this term or this term to get a or c or b, c prime. And this will be the synthesis of the second function f of a, b, c. If we consider a four-variable function f of a, b, c, and d equal, those are just examples, equals to a and c or b all prime, or b exclusive or d. So the first term we have c or b, then we complement this, c or b, then we complement it to get c or b prime, c or b prime, then we end it with a. So what we have? So we have c, this is an OR gate, c or b all prime, so it is an OR gate, c, b, c or b all prime, so it's an OR gate. Now this term will be b and d exclusive OR, so the output will be an exclusive OR. So b exclusive OR d. Now we take this or this will give me the value of f. So the value of f will be a, b, c, f of a, b, c, d will be a, and c nor b prime, or the exclusive OR b and d, the output of the exclusive OR b and d. And this is, again, as a typo here, I'll show you R, which is indication, this is an exclusive OR. Okay. Next slide, we'll talk about combinational network analysis. So we looked at synthesis, quite simple, by using gates. How to do analysis? If we are given a circuit, for instance, okay, we would like to generate its truth table. It's called analysis by generating its truth table. So to find a Boolean function from a given network, it's a truth table. First, we find all the subsequent terms of the function. Then we aggregate all terms to find the function. It would be very helpful to define the network's levels. So this is an example. We would like to find the function f for a given circuit. If we have the function f, also we can find its truth table. So both are called analysis, finding the equation, the switching function f is a function of variables, is a function of the input variables, and finding its truth table. Both are called analysis. So we'll talk about finding the function first, then we'll talk about constructing truth table. So here we have an AND gate G1, the output will be AB. We have another AND gate G2, this is called a two-level circuit, CD. In the third level we have AB or CD, so the value of F will be simply AB or CD. Now to construct the truth table, the Boolean expression F has n switching variables that are 2 to the power n combinations. So a truth table is constructed with 2 to the power n rows with the values of all the switching variables on the left side and the values of the expression of the output function f on the right side. Now we'll take an example to understand this. Let's take with the truth table. So I have the input 3 input variables a, b, and c. So I will fill up the truth table. I will put line to signify the output f. Now c will be the least significant bit, so we alternate 0, 1, 0, 1, 0, 1, 0, 1. We have 8 rows. Why? We have 2 to the power 3 will be equals to 8. B, then we fill up B, the next bit, which is 0, 0, 1, 1, 0, 0, 1, 1. And the most significant bit will be 4 zeros and 4 ones. 0, 0, 0, 0, 1, 1, 1, 1. How we evaluate the value 0? We go through every row and we apply those to the function f. So we have, for instance, when the variables a is 1, b is 1, and c is 1, the value of f will be 1 prime and 1, or 1 and 1, or 1 and 1 prime, which is 0 and 1, 1 and 1, or 1 and 0, which is 0 or 1 or 0, which is equals to 1. So the value of the function f will be 1. We repeat this to every row, and we can fill up the table for f. And you can repeat actually for every row by applying the equation, and you find the output. Or, on the other hand, we can evaluate every term. We have the inputs. I need A prime, I need A prime C, I need AB, I need AC prime, so I need C prime, then I need AC prime, then by using AND operation, then I will use OR operation on those three terms, A prime C, AB, AC prime. For instance, to find A prime, we will find the complement of the function, so we will complement every, okay, will complement every value of A. So 0 will become 1, 0 will become 1, 0 will become 1, 0 will become 1. Then 1, 1, 1, 1 will become 0, 0, 0, 0. The same thing for the C. It is 0, 1, 0, 1, 0, 1, 0, 1. It will become 1, 0, 1, 0, 1, 0, 1, 0. Then we take A prime C. We will AND A prime, which is this row, with C. So 1 and 0 will be 0. 1 and 1 will be equal to 1. And so on and so forth. So generate another 1 here, because 1 and 1 also will be equal to 1. Then all other 0. We generate the same thing, AB. AB could be found from here. 0 and 0 is 0. 0 and 0, 0, 0 and 1, 0, 1 and 0 is 0, 1 and 0 is 0, 1 and 1 is 1, and 1 and 1 is 1. So you generate two ones here. The same thing we do AC prime. We will end this column A with C prime. So 0 and 1 is 0. Okay, then we'll generate all zeros. Then this one will be generated with A, which is 1, and C prime, which is 1, and we'll generate 1. This is the only one generated. Then F, we will OR those three bits, A prime C or AB or AC prime, which is by definition, this is the value of the F given in the example. So we'll get 0, OR 0, OR 0 is 0. 1 OR 0 is 0 is 1. OR gate will give me 1 if at least 1 is equal, one variable is equal to 1. And by this, we will have the value of the function F. Now, we actually use the complement, and the next slide will use the complement F. The complement of F of prime, actually, of any set of input variables is a function whose value is 1 whenever the value of F is 0. So if this in the post table here for the function A prime C or AB or AC prime, we have the function is 0, 1, 0, 1, 1, 0, 1, 1. We'll complement the value for every row. If the function is 0, it will become 1. This is the complement of F. If 1 becomes 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, and 1, 0. So F prime will be the complement of the function F. And as an example, we would like to construct the truth table for the function a, b, or cd. Again, here we will calculate the term ab, we'll calculate cd. This is a 4-variable function. As you can see, the truth table will be 0, 1, 0, 1, 0, 1 for d. Then 0, 0, 1, 1, 0, 0, 1, 1 for C. So 4 zeros and 4 ones, 4 zeros and 4 ones, then 8 zeros and 8 ones to fill out the full combinations. We will add A and B. So A and B will become 1, 1, 1, 1 here at the end of the table when both A and B are 1s. And we will calculate C and D. 0 and 0 is 0, 0 and 1 is 0, 1 and 1 is 1. This is CD. Then we calculate F by ORing A, B, and CD. So 0 or 1 is 1, 0 or 0 is 0, 0 or 1 is 1, and so on and so forth. Whenever there is at least 1, the OR gate will give me 1. If at least one variable is 1, the output will be 1. Then the complement, we will complement every bit. You see in F, complemented to 0 will become 1, and 1 will become 0. So 0, 0, 0 will become 1, 1, 1. This one will become 0. This 0 will become 1, so on and so forth to the end of the table. And this will be the next slide in lecture 5. I would like to thank you so much for listening. Please subscribe, and hopefully I will see you very soon. Sincerely, Dr. Hassan. To subscribe, please click on the logo, which is a blue circle with the letter I inside it. Thank you so much.